It is important for the following portion of the course that the student has an understanding of the operation and configuration of GE Multilin's Universal Relay. Attendance of either the Universal Relay Platform or Maintenance courses, or review of the UR Apps 1 training CD will provide the necessary foundation. In this section of the course, we will examine the capabilities, hardware, and software options of the Universal Relay's Direct I/O service. We can define a direct output as the status of a binary point, for example a contact input, which is transmitted by a universal relay from one of its communication ports. The status of this direct output can be received and stored in a memory location within other universal relays. This would be referred to as a direct input. Collectively, direct inputs and outputs are referred to as direct I/O. The speed with which the transmission and reception occurs is very fast. This has allowed direct I/O to replace interlocks, which were traditionally formed by wiring inputs and outputs of relays together. The direct I/O data exchange service uses a proprietary protocol. Each relay can broadcast the status of up to 32 direct outputs. The direct outputs are broadcast from a relay anytime one direct output changes state. The relay will also rebroadcast direct outputs if a change in state hasn't occurred within the last second. This broadcast without any state change is called an integrity message. Each universal relay on the direct I/O LAN has the potential to receive an entire 32 direct output broadcast. However, usually the receiving relay is programmed to receive only the direct outputs that it is interested in. These direct outputs are received into one of the local relay's 32 direct inputs. If a relay fails to receive a new direct output broadcast, it sets an internal flag within seconds corresponding to the relay which failed to broadcast. The receiving relay then sets the corresponding direct inputs to a per-configured default state. Direct I/O cards, also referred to as Type 7 cards, come in several interface standards. Fiber and RS-422, which we're already familiar with from earlier in the CD, along with G.703 and IEEE C37.94. G.703 is a CCITT communication standard used for interconnecting data communications equipment such as bridges, routers, and multiplexers. The protocol specification for G.703 indicates the transmission media to be wire. IEEE C37.94 is an optical fiber interface standard which has been in use within teleprotection equipment for many years. When the components of a protective relaying solution require commands to be sent between devices, the communications and protection equipment involved is often referred to as teleprotection equipment. All of these communication cards are available in either single or dual port configurations. The ports are referred to as channels in GE Multilin documentation. The dual-channel cards can be of the same or different interface standards. For example, there is both a dual-channel fiber card and a dual-channel card that is composed of a fiber channel and an RS-422 channel. Here is a current list of direct I/O communication cards that are available for the Universal Relay. You can refer to the most recent Universal Relay Instruction Manual for the latest card offering. Point-to-point, single and/or dual-channel ring topologies are available depending on the communication cards chosen. When the communication link and all data transmissions are between only two devices, the topology is referred to as point-to-point. The topology is called single ring when the communication link connecting the devices forms a ring such that transmissions from any device take only one path and travel in one direction around the ring, being relayed from one device to the next until finally returning to the originating device. The topology is called dual ring when a device's transmissions take two paths and can travel in both directions around the ring, again being relayed from one device to the next until finally returning to the originating device. Most all communication cards support a point-to-point topology, but are normally configured to operate in a ring topology such that a failure of the ring can be detected by all relays when transmissions fail to return to the device they originated from. All single-channel fiber optic cards, excluding IEEE C37.94, support a single ring topology of up to 16 universal relays, while dual-channel fiber optic cards, again excluding the IEEE C37.94, support a dual ring topology of up to 16 universal relays. The single and dual channel fiber optic modules use ST connectors. When using a high-power interface, such as laser, devices called attenuators may need to be installed between the transmitter and receiver to attenuate or reduce the intensity of the light to ensure that the maximum optical input power to the receiver isn't exceeded. Here we can see the configuration for the 72, 73, 7D, and 7K fiber laser modules. Let's take a look at the speed or performance of the direct I/O single and dual ring configurations. The timing is very different for single-channel cards as compared to dual-channel cards. With single-channel cards, direct output messages are sent in only one direction. When a message is received by a module from which the message did not originate, it will forward the message on to the transmitter. The message delivery time is approximately 0.2 of a power system cycle at 128 kilobits per second, times the number of bridges, otherwise known as media converters, existing between the origin and destination. Here we can see the expected delivery times for a single healthy ring configuration with a LAN speed of 128 kilobits per second. Notice how the delivery time increases by 0.2 of the power system cycle for every relay the message passes through. If the ring is cut, Relay 1 will know that there's a problem with the communication link, because it will no longer receive the originating message back from Relay 4. Communication cards that support two channels send the direct output messages from both channels simultaneously. If wired correctly, this means that the messages are sent in both directions around the ring. Notice how the delivery time for the message from Relay 1 to Relay 4 is now 0.2 of the power system cycle, which is 1/3 of the time we saw for the single ring configuration. If one of the rings breaks, for example between transmitter 2 of UR1 and receiver 2 of UR4, the expected delivery times match those of a single ring configuration. There is a drop in performance, but the dual ring allows communications to continue. As stated earlier, an integrity message is sent at least once every second to let receiving relays know that the broadcasting relay is still working, even if there is no state change. Single and dual channel communication modules can also be intermixed when forming a LAN. Here we can see 3 universal relays connected using 2 single-channel cards and 1 dual-channel card to form 2 separate rings. Within the EnerVista UR setup software, we can enable the Direct I/O channel crossover setting to allow the Direct I/O to be shared by both rings. In this example, this setting should be enabled on UR number 2. Once enabled, UR2 will forward messages received on Receive 1 out on Transmit 2 and messages received on Receive 2 to be forwarded out on Transmit 1. This will allow all relays to have access to all direct I/O data. Until now, we've looked at the direct I/O service between universal relays that are directly connected together. A direct I/O service can also be provided between several LANs using multiplexers. A multiplexer is a device that is commonly used to set up a communication link between substations. If a link exists between several substations using multiplexers, the RS-422, G.703, or IEEE C37.94 communication interface will allow the direct I/O service to be implemented over these wide area networks if the multiplexer supports these interfaces. In this section, we will look at the G.703 module's interface wiring. The G.703 baud rate is fixed at 64 kilobits per second. This diagram shows the interface wiring. A cable consisting of 2 twisted pairs of shielded number 24 gauge wire is recommended. The shield should be grounded at only one end by the connection to either pin X1A or X6A, as both of these pins are internally connected to ground. It is important to note that the pin identification from other manufacturers may differ from what is shown here. A second common pin identification scheme uses Transmit A, Transmit B, Receive A, and Receive B. If this is the pin identification being used, it can be assumed that the A is equivalent to the plus sign and B is equivalent to the negative sign. We will now go through the procedure to set up the G.703 timing. First, ensure that the control power has been removed from the relay. The ejector inserter clips located at the top and at the bottom of each module can then be pulled simultaneously in order to release the module for removal. Record the module's location. Now, undo the module cover screw and slide the top towards the rear of the module and then lift it upwards to remove it. Now the timing selection switches for Channel 1 and Channel 2 can be set. If the G.70 III interface is to be connected to a higher order system, such as a multiplexer, octet timing is necessary. If this is the case, it would be enabled by setting dip switch 1 to the on position. When two universal relays are connected together, the octet timing should be disabled by setting dip switch 1 off. There are two timing modes for the G.70 III module: internal timing mode and loop timing mode. For UR to UR connections, internal timing mode should be used and can be enabled by setting dip switch 5 to on and dip switch 6 to off. For connection to a higher order system, such as the connection to a multiplexer, the module should be set to loop timing mode by setting dip switch 5 to off and dip switch 6 to off. Now we can replace the top cover and the cover screw. The module can then be reinstalled into the correct slot position. The ejector inserter clips located at the top and at the bottom of each module must be in the disengaged position as the module is smoothly inserted into the slot. Once the clips have cleared the raised edge of the chassis, engage the clips simultaneously. When the clips have locked into position, the module is seated correctly. The 7E, 7F, 7G, 7Q, and 7.5 modules have a 64 kilobit per second G.70 III interface and a fiber interface. They can be used in configurations where Channel 1, which is the G.70 III interface, is connected to another device's G.70 III interface, such as a multiplexer. In this configuration, Channel 2 is a standard fiber interface for local connection to other UR relays. Delivery time for direct I/O messages is approximately 0.4 of a power system cycle at 64 kilobits per second for each bridge. The UR series that have a firmware version of 3.30 or higher can support the IEEE C37.94 communication modules 7.6 and 7.7. These modules are designed to interface the Universal Relay's direct I/O with IEEE C37.94 compliant digital multiplexers and interface converters. This standard defines the communication link as a point-to-point optical link for synchronous data between a multiplexer and teleprotection equipment with a fixed baud rate of 64 kilobits per second. The optical fiber interface is compatible with multi-mode fiber optic cable having a 50 or 62.5 micrometer core diameter, ST connectors, and a light wavelength of 830 nanometers plus or minus 40 nanometers. The delivery time for direct input-output messages with this interface is approximately 0.4 of a power system cycle at 64 kilobits per second for each bridge. The transmitter of the module is connected to the receiver of the multiplexer using compatible connectors and vice versa. This interface requires that one of the two devices on the link provide the system clock timing signal. The Universal Relay's IEEE C37.94 module has the capability of generating the timing signal or deriving the timing signal from the received line signal. The setting of a group of dip switches on the module determines whether or not the module will provide the timing signal or derive it from the received signal. When the dip switches are set to internal timing mode, the system clock is generated internal to the module, and when set to looped timing mode, the module derives the system clock from the received line signal. To have correct operation in this example, the timing switch selection from one of the relays should be set to internal timing and the other to loop timed. To access the dip switches, the communications module must first be removed following the procedure described earlier in this section. Once the module is removed, set the timing selection switches, Channel 1, Channel 2, to the desired timing modes. Now the module can be replaced. The RS422 Direct I/O interface has a fixed baud rate of 64 kilobits per second and requires an external square wave clock signal in order to work. The RS422 module delivery time is approximately 0.4 of a power system cycle at 64 kilobits per second for each bridge. It's important to verify that the interface connected to the RS422 module samples data during the rising edge of the 64 kHz transmit timing clock. This means that the clock's rising edge will be in the middle of the bit time. The objective of this lab is to familiarize the student with the software setting options for GE Multilin's Universal Relay Direct I/O modules and demonstrate how to set up and configure the Direct I/O service between two universal relays such that the status of Control Push Button 1 will be sent by Universal Relay 1 via the Direct I/O service to Universal Relay 2. The second relay will then display the status of Control Push Button 1 on a user-programmable LED. To complete this lab, we'll need two universal relays with Type 7C communication modules, along with a single pair of 62.5 by 125 micrometer multi-mode fiber optic cable terminated in ST connectors. First, we'll connect the 7C communication modules together and power up the relays. Launch the InterVista UR setup software, and from the Product Setup menu, select the Direct I/O submenu. The first three entries, device ID, ring function, and data rate, are the critical settings, with the rest being optional. The device ID is a unique number between 1 and 16 that must be assigned to each relay within the Direct I/O LAN. All direct output messages from this relay will contain the device ID entered here. This number is used to identify the sender of the direct output message. We will enter 1 as the device ID for Relay 1 and 2 for the second relay. If the channel ring function is set to yes, the Direct I/O scheme will be configured to operate in a ring, meaning that the module expects all direct output messages sent by the module to be received back at the receiver input. If not, the module's direct input-output ring break self-test will be triggered, and the direct ring break flex logic operand will be set to a logic 1 state. For our application, we will select yes for both relays. We will set the Direct I/O data rate to match the data capabilities of the communications channel. When the universal relays using the fiber optic communication interfaces listed are connected directly together, the baud rate may be set to 128 kilobits per second. For local relays configured with all other communication cards, the baud rate will be set to 64 kilobits per second. All universal relays communicating over direct inputs-outputs must be set to the same data rate. Dual-channel communication cards apply the same data rate to both channels. Note that the G.703, RS422, and C37.94 modules are fixed at 64 kilobits per second. The Direct I/O data rate setting is not applicable to these modules. Since we're using fiber cards, we will set the Direct I/O data rate to 128 kilobits per second. The Direct I/O channel crossover setting applies to universal relays with dual-channel communication cards and allows crossing over of messages from either channel. Once enabled, the card will forward messages received on its Receive 1 out Transmit 2, and messages received on Receive 2 will be forwarded out on Transmit 1. This will allow all relays connected to this relay's Channel 1 or Channel 2 to have access to all Direct I/O data. This option isn't shown with a single-channel card. The channel CRC alarm count threshold function is used with cards that use copper wire for external connections to detect corrupted messages due to electromagnetic interference. The CRC alarm function works as a separate function on each channel. The universal relay checks the integrity of the incoming direct input-output messages using a 32-bit CRC. When enabled, the CRC alarm function tracks the rate of CRC messages failing the CRC. It accomplishes this using two counters. The first counts all incoming messages, including messages that failed the CRC check. The second counts only those messages that failed the CRC check. If the number of messages that failed the CRC check reaches the user-defined level specified by the CRC alarm channel threshold before the CRC alarm channel count value is reached, the Direct I/O channel CRC alarm flex logic operand will be set to the on state. This change of state should trigger a fault message, such as a digital element or a user-definable LED. When the total message counter reaches the count entered into the CRC alarm channel message count setting, both the counters reset and the monitoring process is restarted. Note that the total number of Direct I/O messages that failed the CRC can be monitored in the following way. From the Actual Values menu, select Status, then Direct Inputs, and finally CRC Fail Count. This should be observed during normal operation to determine settings. Since we're using fiber interfaces, the channel CRC alarm function will be left disabled. The universal relay checks the integrity of the direct input-output communication ring by counting unreturned messages. In the ring configuration, all messages originating at a given device should return within a predefined period of time to that device. The unreturned messages alarm function is available for monitoring the integrity of the communication ring by tracking the rate of unreturned messages. This is accomplished in a similar fashion to the CRC alarm. When enabled, this function counts all the outgoing messages, and a separate counter counts the messages that have failed to return. If the unreturned message counter reaches the value entered as the message alarm threshold before the total message counter reaches the count entered as the message alarm count, the direct I/O channel unreturned alarm flex logic operand is set. When the total message counter reaches the message's alarm count setting, both counters are reset and the monitoring process is restarted. The total number of unreturned messages is available. To monitor this count, go to the Actual Values menu and select the Status submenu, and then select the Direct Inputs menu, and finally select the Unreturned Message Count for Channel 1 or Channel 2. We're using a ring topology, and so the channel message alarm function will be enabled with the channel message alarm count and the channel message alarm threshold set to the defaults of 600 and 10 respectively. Here we can see the final setup of the Direct I/O submenu for Relays 1 and 2. Ensure that these settings are saved. We must now configure Control Push Button 1 of Universal Relay 1 to drive the status of a direct output. From the Product Setup menu of Relay 1, select the Control Push Button menu, and then enable Control Push Button 1 and save. Now that Control Push Button 1 is enabled, we will configure the relay to use the status of this Control Push Button to drive direct output number 1. From the Inputs-Outputs menu, select Direct Outputs. In the Direct Output menu, the user has access to the 3 user-configurable settings for each of the 32 direct outputs. The first setting is the Direct Out 1 name. This setting allows the user to assign a descriptive name to the direct output. This name will appear in the flex logic operand associated with this direct output. We'll leave this setting at its default. The Direct Out 1 operand setting allows the user to select a digital flex logic operand whose state determines the state of this direct output. We want direct output 1 to go to the logic 1 state when Control Push Button 1 is pressed, and so we'll set direct output 1's operand to Control Push Button 1 on. The event setting enables or disables event logging of the change of state of the associated direct output. Save these settings. Once these settings have been saved, each time the Control Push Button 1 is pressed, direct output 1 changes to a logic 1 state. This will cause the relay to broadcast the status of all 32 direct outputs. This relay will automatically rebroadcast the status of the direct outputs if a second passes since the last broadcast. This is referred to as an integrity broadcast and is used to inform other relays on the direct I/O LAN that this relay is still active. We must now configure relay number 2 to store the status of relay 1's direct output 1. This status will be stored in relay 2's direct input 1. Relay 2 will also be configured to display this status on a user-programmable LED. From Relay 2's Inputs-Outputs menu, select the Direct Inputs submenu. Within this menu, you'll be presented with 6 configurable settings for each of the 32 direct inputs. The Direct Input 1 name entry allows the user to assign a descriptive name to the direct input, which will appear as part of the flex logic operand name for this input. The device corresponds to the device ID of the relay sending the direct output. In our case, the direct output we're interested in is being broadcast from Relay 1, whose corresponding device ID was set to a value of 1, and so 1 will be entered here. The number entry allows the user to specify which output of the direct output broadcast message from the specified device will be stored as this direct input. We're interested in direct output 1, and so 1 is entered here. The direct input default state represents the state of the direct input when the associated device is offline. Several choices are available. Setting the direct 1 default state to on defaults the input to logic 1. A setting of off defaults the input to logic 0. A setting of latest on freezes the input in case of lost communications. If the latest state is not known, such as after relay power-up but before the first communication exchange, the input will default to the on state. Finally, a setting of direct input 1 default state to latest off freezes the input in case of lost communications. If the latest state is not known, such as after relay power-up but before the first communication exchange, the input will default to the off state. In our example, we'll set the default state to off and then save the settings. As a final step, the user-programmable LED 1 on Relay 2 will be configured to display the state of direct input 1. To configure this LED, go to Relay 2's Product Setup menu. Select the User-Programmable LEDs menu, and then select the User-Programmable LEDs submenu. Select Direct Input 1 On as the operand for LED number 1, and select the Save command. Now, if all the steps were completed correctly, each time Relay 1's Control Push Button 1 is pressed, the User-Programmable LED 1 of Relay number 2 will come on. To monitor the message return time, unreturned message count, and CRC message failures, open the Actual Values menu and select Status, then Direct Inputs. As stated earlier during the configuration portion of the lab, the failure of the fiber optic ring will be detected by all universal relays. To demonstrate this feature, the student can disconnect one of the direct I/O fibers and note that the message Direct Device Off will be immediately displayed on both universal relays' LCD displays, in addition to the illumination of the trouble LED. Both relays have detected the failure. When the fiber is reconnected, both fault indications will no longer be displayed. This completes our direct I/O lab exercise.